Think about the infrastructure that runs your digital life. It is built on invisible foundations. We rarely stop to consider the moment a program requests a piece of memory, yet that single action determines whether an application runs smoothly or collapses under pressure. For years, the industry has relied on a standard default allocator built into the Linux operating system. It works well for most general-purpose tasks, but when you scale to the size of Meta, the defaults become bottlenecks. This is where the renewed commitment to jemalloc becomes critical. Jemalloc stands for the Memory Allocator. It is a custom-built memory management system designed specifically to handle high-performance workloads. The decision to invest heavily in this technology signals a strategic pivot. It suggests that Meta is moving away from reliance on external standard libraries toward a deeply integrated custom solution optimized for their specific workload patterns. This is not just a software update. It is a fundamental shift in how they manage the lifeblood of their infrastructure. Here is the thing you need to understand about this transition. It is a classic case of pay-to-play. You gain performance, but you pay a steep price in engineering complexity. Standard allocators like the one found in the GNUC library are designed to be general purpose. They are safe, they are compatible, and they require little maintenance, but they suffer from fragmentation. Over time, as memory is requested and released, gaps appear in the memory space. The system has to search further and further to find a contiguous block of space. This slows everything down. Meta faces a different reality. They run massive distributed systems where latency matters more than anything else. Every microsecond counts. If the allocator spends too much time searching for free memory, the entire application slows down. This is where the custom approach pays off. By controlling the allocator, Meta can tune the behavior to match their specific access patterns. They can reduce the time spent on synchronization and minimize cache pollution. Now consider the implications for multi-threading. Modern applications run on many cores simultaneously. When multiple threads request memory at the same time, the system must prevent them from stepping on each other. This requires locking mechanisms. Standard allocators often use coarse locks that become a point of contention. Imagine a single toll booth on a highway where thousands of cars need to pass. Everyone has to wait. Jemalloc uses finer-grained locks or lock-free algorithms. This allows multiple threads to allocate memory without waiting for a single central authority. The cost of this optimization is significant. Maintaining a custom allocator requires a dedicated team of engineers. They must handle security patches, compatibility issues, and performance tuning. This is the pay-to-play cost. Most companies cannot afford this overhead. They accept the performance hit of the standard allocator to save on engineering resources. Meta is choosing to absorb that cost because the performance gain is essential for their business model. There is also a critical dimension regarding memory safety. Memory corruption is a leading cause of security vulnerabilities. When an application writes to a memory address it does not own, it can crash or allow malicious code execution. Standard allocators provide some protection, but they are not foolproof. A renewed commitment to a custom allocator often includes formal verification efforts. This means the logic of the allocator is mathematically proven to be correct. It reduces the attack surface of the system. This brings us to the broader industry trend. High-performance systems are increasingly prioritizing fine-grained control over memory fragmentation and latency. They are accepting the trade-off of increased engineering complexity to gain stability at scale. We are seeing a move away from one-size-fits-all solutions. The standard library allocator is no longer sufficient for massive-scale multi-threaded applications. Future implications suggest that Meta's internal optimizations will drive the next generation of open-source allocator standards. Concepts like star malloc, which focus on formal verification and concurrency, are likely to influence how large-scale distributed systems handle security and performance. The renewed focus indicates that existing memory allocation bottlenecks have become critical performance constraints. This necessitates a return to foundational infrastructure improvements rather than higher-level application tweaks. You might wonder if this applies to your own work. If you are running a small service, the standard allocator is probably fine. But if you are managing high-throughput systems, the cost of the standard allocator is hidden in the latency of your requests. The decision to invest in a custom solution is not about novelty. It is about recognizing that the foundation must support the weight of the structure above it. The research into this area highlights a significant gap in general knowledge. Many developers assume the standard library is the only option. The reality is that for massive scale, custom allocators are essential for maintaining throughput and reducing garbage collection pauses. This is not a secret, but it is often overlooked in favor of higher-level optimizations. In the end, this strategic pivot reflects a maturing of the industry. We are moving past the era where software could rely on the operating system to handle everything. The gap between what the hardware can do and what the software requests is too wide to ignore. Meta's commitment to jemalloc is a signal that the future belongs to those who control their own infrastructure at the lowest levels. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.